In my previous video, I talked about how to build an AM radio receiver. I used a homemade speaker in that video, but did not like how it sounded. In this video, I'll be focusing on all aspects of understanding and building a professional and great sounding speaker. Let us get started with the concepts. When you hear a sound, you're experiencing air pressure vibrating in your ears. Sound travels in a longitudinal wave, and what that means is that the wave's peaks and troughs move side to side. The peaks are called compression, and the troughs are called rarefaction. So a speaker uses a diaphragm that vibrates where the pushes create air compression and the pulls create air rarefactions. When the air pressure wave reaches your ear, the eardrum vibrates and informs the brain that music from your speaker is playing. There are many parts to a sound wave. First is the amplitude, which signifies the intensity of the air's compression. The higher the intensity, the higher the volume. Next, it has a frequency, which is how many times the compression and rarefaction happen in a second. At lower frequencies, fewer compressions are observed in a second. At higher frequencies, more compressions are observed. The human ear can hear sounds with frequencies between 20 Hz and 20 kHz. The lower frequencies are called bass, and this is what a drum or tuba at a lower octave produces. The higher frequencies are called treble, and this is what a violin or flute at a higher octave produces. You will soon see that bass and treble have significant impacts on speaker design. In fact, we use completely different types of speakers to play each of them. Sound travels at 767 miles per hour. It's actually a lot slower than radio waves. In addition, sound needs air to propagate. So, you may ask, how did the astronauts communicate with us when they landed on the moon? And the answer leads us to how a speaker works. It takes the electrical waves that vary in voltage with time and converts them to sound waves that match the exact wave form. Higher the voltage, higher the loudness. One wavelength of the input AC wave matches one compression and rarefaction of sound. And now, we are ready to build our own speaker. So our goal is to take the audio signal that varies with voltage with time and convert it into displacement. If the displacement can exactly match the peaks and troughs of the voltage with time audio signal, we'll have an ideal speaker. Physics has provided us with a solution for what we need. If we get a coil that's carrying current, it can generate a magnetic field. If we curl our fingers in the direction of the current, the magnetic field generated is along the axis of the coil. If we reverse the direction of the current, the polarity of magnetic field also reverses. If we increase the current, the strength of the magnetic field also increases. By connecting the coil to an audio signal, we could switch the magnetic field synchronously with the audio signal. Now, by placing a permanent magnet that's axially magnetized, and have it interact with the coil on the same axis, the coil is either attracted or repelled from the permanent magnet based on the polarity of its magnetic field, which in turn depends on the direction of the current of the incoming audio signal. Let's do an experiment. Here's an experiment that recreates what we discussed earlier. We have a neodymium magnet with a 30-gauge copper coil around it. These are connected to a simple circuit with a potentiometer of a linear taper and a battery. If I increase the current to the coil, it will rise. And if I decrease it, it will fall back down. If we can connect these to a membrane, they can vibrate and produce sound waves. Before we embark on our journey to build a prototype speaker, I would like to clarify a common misconception that speakers work due to Faraday's law of electromagnetic induction. Faraday's law states that whenever a conductor is placed in varying magnetic field, an electromagnetic force is generated, which in turn creates a current in the coil. The converse is also true. It is a common misconception that the varying current in the coil generates the magnetic field that interacts with the permanent magnet. This is certainly not true, as I showed in my experiment that a DC voltage is sufficient to induce a magnetic field on the coil. However, Faraday's law, or in particular, Lenz's law, does impact speaker performance by generating something called back EMF. We'll get to this later in the video. Before we build a speaker, let us look at the parts of the speaker. The coil that carries the current is called the voice coil, and it interacts with the permanent magnet on the base of the assembly. They're the most important parts of the speaker. A fabric, called a spider, suspends the voice coil on the top of the magnet. A cone, also called a diaphragm, is connected on top of the voice coil, and it oscillates with the voice coil. It pushes the air to create sound waves. The entire assembly is housed in a casing called a basket, and the cone is attached to the basket using a flexible gasket called a surround, also called a suspension. Optionally, the top of the voice coil can be covered with a dust cap to protect the voice coil and magnet inside. So here's what you'll need to make your speaker. First, here's a magnet that I am going to use. So it is a 40 millimeter neodymium magnet, and you can have a little look at it. I'll link it in the description. Now for the voice coil, I 3D printed this former. It's 42 millimeters, and the magnet is 40 millimeters. So this one will fit with a 2 millimeter gap, which means it's pretty loose, and this is very important. Now here, this is a casing that I made, and it's also known as a chassis, and it can also fit both the magnet and the voice coil. Now this part over here is the spider, and it will connect to the voice coil, and it will suspend the voice coil. Now the suspension of the voice coil also means that the voice coil can only move up and down and won't be able to easily move side to side. Now to encase everything, I'm using this basket over here, and it will be able to hold the spider and the cone. Now also, one more thing you'll need is this wire, and this wire's main purpose is to wind the voice coil. Now this is 30 gauge, and this is the label. And for the cone, you'll need a foam paper bowl, and this will fit over the basket. So the first step to make your speaker is to glue the magnet inside the chassis. It's important to make sure that your magnet is as centered as possible. So now that it's glued in the center, next step is to take the basket and to drill a hole big enough to fit the chassis inside. The voice coil is going to go inside through that hole and bounce up and down. So I connected the chassis to the basket. This is what it looks like. So now it's time to create the voice coil. So right now we're winding the first layer of the coil, and soon we'll start winding the second. So this is the finished voice coil. It has 2 layers on it, and it was quite an arduous process to wind it, so I wasn't able to capture it on camera. It's 15 millimeters wide. Next, let's suspend the voice coil using the spider. I've enlarged the hole on the spider to make it fit snugly around the voice coil. I've also printed this ring that we can use to attach the spider into the speaker basket. So I've attached the spider to the ring. The next step is to glue the spider to the basket and the voice coil. It is very important that the voice coil is suspended accurately on the magnetic gap. As you can see, I wrapped a few greeting cards around the magnet so that the voice coil is positioned correctly. I also positioned the voice coil so half the length of the winding stays above the magnet while the rest stays inside. We have finally attached the voice coil to the spider. As you can see, the voice coil fits nicely around the magnet. Next, we're going to drill holes to run the leads from the voice coil, and we'll also connect the speaker cone to the voice coil. So here's the final version of our prototype speaker. As you can see, I attached some wire anchors and attached them to the basket. The gasket is also attached. I originally did not plan on using a dust cap, but I changed my mind to make it look more appealing. I used a travel-sized container for the cap that exactly fits the voice coil. I also used some yellow craft paper to cover some of the blemishes on the paper cone. Okay, so now let's put the speaker to the test.
Tell me more, obviously. To continuously attract and eliminate flying insects. Take that, bugxiety, and don't miss Teenage Mutant Ninja Turtles, only in theaters August 2nd.
As you saw, the speaker driver works quite well, but I did hear some bass distortions that can be improved. If you thought building a speaker driver is a work of art, you're not mistaken. While we discussed the basic laws of physics, most of what we did was a work of art. But I'm a scientist, and let me put on my scientist hat. Now, I'm going to tell you that this is the absolute wrong way to build a speaker. Just as if you were wondering if we're done building a speaker, let me tell you this is just where our journey starts. We're going to dissect every part of our speaker and investigate each component and explore every mistake we've made. So keep your seatbelts fastened as we get into cruise control. Speakers are broadly classified into three ranges. The tweeter range, which has an operating range from 1 kHz to 10 kHz, the woofer or mid-range speaker, which works between 200 Hz and 2 kHz, and the subwoofer speaker, which works best at less than 500 Hz. This classification is directly correlated with how our hearing system works. We are actually not very sensitive to the range of 0 to 200 Hz. Some examples of frequencies in this range are the drums or a tuba playing. This means that we need a lot of membrane displacement and in turn stronger compressions and rarefactions to hear them. The subwoofer speakers target this range. They have a large speaker cone and displace a lot of air to make them audible to our ears. We're most sensitive to the 1 kHz to 3 kHz range, and some examples are the sounds from a piano or violin. These don't need a lot of membrane displacement for our ears to hear them. The tweeters target this range, and they're the small speakers placed in your car or the loudspeakers. The range from 200 Hz to 2 kHz are the mid-range speakers, and they may be sufficient for most needs. Not too large and not too small, and they cover most of what we want to hear. And finally, the upper ranges above 5 kHz are quite undesirable to hear, though our ears are still sensitive to them. Now, let us look at the key performance indicators that are used to grade a speaker. The first one is speaker sensitivity, which directly relates to loudness. Speaker sensitivity is a measure of how well a speaker converts amplifier power to sound pressure. Sound pressure level, or in short SPL, is measured by placing a microphone at the distance of 1 meter with 1 watt of power coming from the amplifier. Its units are decibels. To correlate decibels to loudness, a soft whisper is around 30 decibels. A normal conversation with another person is about 60 decibels. A good loudspeaker that fills a large room can do about 80 to 90 decibels. And anything over 100 decibels is perceived as very loud, like a jet plane or lawnmower. Decibels use a logarithmic scale, and what that means is when sound intensity doubles, the sensitivity increases by 3 decibels. A loudspeaker with a sensitivity of 90 decibels will have twice the sound intensity as one with 87 decibels. It's also important to note that our ear responds differently to woofer and tweeter frequencies. The SPL measurement is weighted to account for this. Some speakers use a frequency response graph to directly plot the SPL response of a speaker for the entire frequency range. Next, let us talk about the electrical characteristics of a speaker. They are power and impedance, and as a matter of fact, they are strongly correlated with each other. Let us delve into each of these characteristics. A speaker is always matched to an amplifier that is driving it. The amplifier provides power to the speaker, and the speaker converts it into sound pressure level, or SPL. But before we delve into power, we need a detailed understanding of speaker impedance. Here, I have many voice coils I got from eBay. As you can see, they're of different sizes, but they're either graded as 4 ohms or 8 ohms in impedance. So what is impedance? Impedance is the resistance that the voice coil offers to the current coming from the amplifier. Well, this sounds a lot like resistance, and the unit is ohms, so why not just call it resistance? Well, there is a difference. As you can see, the voice coil looks a lot like an inductor. I talked about inductors in my previous video on building an AM radio receiver. It offers resistance that varies with the frequency of the AC current. In fact, the lowest impedance is measured at DC, where inductance does not have a contribution. However, as the frequency increases, inductance starts to play a contributing role and increases the impedance of the speaker. We can see it in this graph below that plots speaker impedance as a function of frequency. The impedance is fairly constant at lower frequencies but rises at the end as the inductance starts to play a role. A good speaker will try to mitigate the contribution from inductance, and we'll talk about shorting rings later in the video. You can also see a spike known as the resonant frequency. This is inherently a function of how the speaker is built, and being able to mitigate this resonance significantly improves the quality of the speaker. Here's my favorite amplifier, the LM36, which drives the power up to 1 watt to an 8 ohm speaker. Plugging this into our power equation, we'll get 2.83 volts. To get this number, we can simplify this equation to power is equal to voltage times voltage divided by R, which is resistance. Rearranging this, we'll get that voltage is equal to power times resistance square rooted. So if the power is 1 watt and resistance is 8 ohms, the voltage will be 2.83 volts, which is the voltage that is going to be used to drive the speaker. Now, using Ohm's law, which is current is equal to voltage divided by resistance, we can plug in the values that voltage is equal to 2.83 volts and resistance is equal to 8 ohms. The current then will be 0.35 amps or 350 milliamps. Now, let us see what happens if we mismatch speaker impedances. Let us try connecting a 4-ohm speaker to the LM386. The LM386 is still going to assume this is an 8-ohm speaker and drive a voltage of 2.83 volts. Plugging this back into Ohm's law, we're going to get a current of 707 milliamps. This is twice the amount of current that is needed for an 8-ohm speaker. Plugging this back into a power equation, we get the power of 2 watts. You're effectively driving 2 watts to a speaker that was spec'd for 1 watt. While nothing bad is going to happen to the LM386 or the speaker in our case, this can adversely affect other speakers. Let us recap what we discussed earlier. Speakers are classified as woofers and tweeters based on the frequency range they're targeting. An amplifier drives the speaker by providing electrical power to it. This results in current flowing in the speaker's coil. The current is based on the power provided by the amplifier and the impedance offered by the speaker. The impedance of the speaker should match the grading of the amplifier to avoid impedance mismatches, and it should be maintained across audio frequencies to avoid speaker distortions. Finally, the magnetic assembly in the speaker converts the current to sound waves by oscillating its diaphragm. Sound is graded using speaker pressure level or SPL, and it is measured in decibels. Now, let us get into designing woofer speakers. The first thing to look at is the magnetic assembly of the speaker. We'll be using 2 important terms here. Magnetic field is a line of magnetic influence that encompasses experiences with a direction from the north to south pole. Its units are measured in Tesla. Magnetic flux is the total magnetic field that passes through a given area. More the number of magnetic field lines in a given area, the stronger is the magnetic force experienced by an object in the area. Its unit is measured in Maxwell's. As I mentioned earlier, magnetic assembly of the prototype speaker was incorrect, especially when building a woofer. Let us see this in detail. The figure here shows the interaction of the magnetic flux of the permanent magnet with the voice coil. The most critical element here is that we want this magnetic flux to remain the same, as the voice coil oscillates towards and away from the permanent magnet. This is where the prototype speaker falls apart. Clearly, there's no way to maintain a fixed magnetic flux in the air gap that interacts with the voice coil. Let us look at the magnetic assembly of a professional woofer driver. As shown in the figure, the magnetic flux is concentrated on a ring-shaped place called the air gap between the pole pieces. When the voice coil oscillates, it interacts with only the magnetic flux in this air gap, and hence remains constant. The pole pieces play a role in propagating the magnetic flux from the magnet into the air gap. The magnetic permeability and saturation of the materials used significantly impacts the flux. Generally, galvanized iron, raw steel, and 10x8 steel are good materials to use. Stainless steel is a very bad choice. When the voice coil moves in the air gap, the current in the coil is perpendicular to the magnetic field, and it experiences a Lorentz force, which is upwards or downwards based on the direction of the current. This drives the speaker. The equation for Lorentz force is given as force is equal to B, which is the magnetic field, times L, the number of lines of coil in the air gap, times I, which is the current carried in the coil. The amplifier drives the electrical power to the speaker and provides the current in the equation. The rest of the terms B, L is used to grade the magnetic ability of the speaker, and it is termed as speaker, BL. Together, this equation estimates the SPL that the given speaker can generate. There are 2 common magnetic assemblies used in speakers, the pot type and ring type. These assemblies are shown here, but we'll be building a woofer for each one, and we're going to go in further detail at that time. Now, let us look at each part of the speaker in detail. First, let us start with the magnets. Old and vintage speakers use olignomagnets in a pod-type assembly. The current generation speakers use ceramic ring magnets in a ring pipe assembly. Recently, neodymium ring magnets are increasingly used in speakers. Neodymium magnets are a lot more powerful than ceramic magnets of the same size, but also more expensive. Now, let us look at voice coils. As mentioned earlier, the voice coils are graded as 4 ohms and 8 ohms, irrespective of their size, so why not always go with the smaller size? The issue is that the power rating increases, especially for subwoofers. The voice coil conducts a lot more current, and this needs a thicker copper wire. Additionally, the voice coil oscillation with a large current generates a lot of heat. This heat needs to be dissipated in order to avoid voice coil blowouts. Larger voice coils can better handle heat dissipation with a larger surface area. However, large coils with a thicker gauge copper wire can add more weight. For this reason, CCA or copper-clad aluminum wires which are used are much lighter and can also dissipate heat more effectively. As a drawback, CCA wires cannot carry the same amount of current compared to copper wires of the same gauge. Finally, the former we used in the prototype speaker to wind our coil was a bad choice. Plastic can melt with heat. Professional voice coils use aluminum for their former and wrap it with paper to hold coil leads. Next, let us look at the cone. Cones play a significant role in the speaker as they're responsible for creating the compressions and refractions. Generally, paper is a very good choice. Sometimes Kevlar or nylon is used for high-end speakers. Let's start building the pod-type woofer speaker we discussed earlier. I'm using a half-coupling pipe fitting along with a raw steel disc to make the pod assembly. This is how it will look. I'm also using a neodymium magnet that is 30 millimeters in diameter. You can have a look at that too. The centerpiece is another raw steel disc that is 32 millimeters in diameter and will sit on top of the magnet as shown. All the magnetic flux is concentrated in the magnetic gap between the centerpiece and the pod. For the voice coil, I got this from eBay, and I will provide the link in the description below. This one is 34 millimeters in diameter and will loosely fit in the magnetic gap. I recommend buying voice coils in pairs and with multiple diameters since they got shipped from China and has a single shipping cost for the entire package. Okay, let us build the speaker. I'll be using a 2-part epoxy adhesive and super glue to connect the parts together. Since I've already shown how to build a prototype speaker, I'll skip forward with these steps. Also, here's the super glue I'm using, and here is the epoxy. So here is the finished pod assembly. And the next step is going to be to connect it to the basket, and along with that, suspend the voice coil with the spider. But before I do this, I want to check several things. First, I want to check the polarity of the voice coil. And to do that, I'm going to connect this voice coil to the spider so that it stays in the magnetic gap. And then I'm going to put the voice coil in the pod assembly. Now I can connect these two leads to the power source, and in this case I'm using a 9-volt battery. So I can connect the black wire and the red wire, and first we're going to do it randomly. So we're just guessing the polarity, and as you can see, it does not go up. I could connect it fully and it's on, so it's not going up. So this is the wrong polarity. So let's flip it and see what happens. If it's the right polarity, it will jump up and come off the pod assembly. So let's see if that happens. Oh, and there we go. It jumped right off. So this is the correct polarity for our speaker. The next thing I want to check is the impedance for the voice coil. So to do that, I'm bringing back the multimeter, which is right here. And I'm going to connect some alligator clips to the wires, like this, so we can easily connect it to the voice coil. So let's see what reading we get. First, I'll connect it to the voice coil using the polarity that we saw earlier. So that's red and that's black. And then I can turn this on and set it to 200 ohms. And let's see what we get. 7.7. So this is an 8 ohm voice coil. Also, it is important to position the voice coil to align the midpoint of its winding to the midpoint of the centerpiece. I've shown it laterally on this drawing, but the voice coil actually goes around the centerpiece. The thickness of the voice coil is 15 millimeters, and the thickness of the centerpiece is 10 millimeters. In addition, the spider needs to be suspended by 10 millimeters above the centerpiece to give enough room for the voice coil to oscillate around the centerpiece. So, to find the position of the voice coil, we'll first take the thickness of the voice coil, then divide it by 2, then add the thickness of the centerpiece divided by 2, and then add that extra 10 millimeters to get 22.5 millimeters, which is the height from the bottom of the coil to the spider. Another note I would like to make is that I recently made a trip to Walmart, and they had restocked this food bowl, which is smaller and better serves as a speaker basket for our woofer. So I'll be using this basket instead of the white one shown previously. The rest of the steps to build the speaker are similar to how we built the prototype speaker. I've attached the voice coil to the spider, and I suspended the voice coil over the magnet assembly. I also attached wire anchors to the side of the basket to connect the leads from the voice coil to wires that can connect to an amplifier. And the next step is to connect the speaker cone and surround to the basket. So here's the finished pot type woofer speaker, and you can see it turned out quite well. But now it's time to hear whether it sounds well. Now, let us get on to building the ring type woofer we discussed earlier. The ring magnets in a ring type woofer are generally ceramic magnets. They are less strong but also a lot cheaper than neodymium magnets. They're the most common type of speaker driver magnets in use today. However, we're going to do something different. We're going to use neodymium cylinders to line up the ring and form a ring magnet. A lot of new generation speakers have started using neodymium magnets for the ring assembly. This provides a lot more magnetic flux for the woofer. The yoke comprises of a bottom plate made of raw steel, along with a pile fitting, which is going to act as our pole piece. And it has an outer diameter of 33 millimeters. The magnetic flux is concentrated here between the top plate and the pole piece, although there is a possibility that the flux will leak out in the outer circuits here and here. And finally, I'm going to use a 36 millimeter voice coil with an 8 ohm impedance for this driver. Another thing that we have to know while building woofers is inductance distortion. The voice coil is an inductor, and it's oscillating on top of the pole piece, which is an iron core with high permeability. This causes the inductance to rise and fall as the voice coil oscillates. To fix this, we can use a Faraday shorting ring. This is nothing but a copper plate that we wind around the pole piece. The shorting ring cancels the effect of varying magnetic flux from the voice coil oscillations. For this speaker, though, I decided not to use the shorting ring. The magnetic gap was already very tight, and I was not able to get enough tolerance with the shorting ring attached to the pole piece. Now, let us build the ring type woofer. This is our finished magnet assembly for the speaker. And as you can see, all the magnets are lined up in a way to make a ring like this. And now that we finished the magnet assembly, the rest of the steps are pretty straightforward, and I'll build the final speaker and show it to you when I'm done. So this is the finished speaker with a ring type magnet assembly. And it turned out the best of all the speakers I built, and it has a very good bass. Next, let us get into building the more easier type of speakers, the tweeters. As I mentioned earlier, tweeters operate in the range of 1 kHz to 10 kHz, and this is the range that our ears are sensitive. What this means is that tweeters don't need to push a lot of air to make them audible to our ears. In fact, tweeters are much smaller than woofers, and they don't even need a speaker cone. So let's start building one. So the first step is to stick the magnet inside the end cap. And to do that, I'm going to be using this 3D printed former. This 3D printed former will sit inside the end cap and make sure that the end cap or the magnet don't get scratched. So as you can see, I glued the magnet inside the end cap, and I also put the center plate on top of the magnet. Now, the next and last step is to connect this tweeter coil over the magnet. So I unfortunately broke both of the tweeter coils, but thankfully I have this titanium tweeter coil at my disposal, so I'm going to use that. Also, I noticed that the center plate was protruding slightly outside the pot, so I glued this other 836 steel disc over the pot so that we will get a good magnetic gap. So now that we finished the tweeter, let's hear how it sounds. That concludes our video on speaker drivers. I hope you like it. Here are some important resources I used in building this speaker. For magnets, I used kjmagnetics.com. They were very reliable and provided neodymium magnets of all different sizes. I used eBay for voice coils. As mentioned earlier, it's economical to buy multiple sizes and in pairs since there's a single shipping cost. For the yoke and pole pieces, I used Etsy.com and the vendor 222 Steel. They have a good availability of raw steel discs and plates, and the workmanship was very good. I used Home Depot for the central pole pieces. They were male-to-male galvanized iron pipe fittings. And that's all. Thank you for listening.